You ever, really stop and think about how things change? I'm not talking about big, dramatic stuff, but, the little transformations that happen all around us. Like a bike getting rusty in the rain, or even the food we eat that gives us energy. Well, it turns out there's a hidden language that describes all of it. And today, we're going to learn how to speak it.
Okay, here's a question for you. What does a rusty old pan have in common with the lunch you just ate? I know it sounds like a weird riddle, right? But believe it or not, the answer connects almost everything in our world, and it's literally happening inside you as we speak.
And there it is. They are all chemical reactions. That's the secret. When milk goes sour, that's a chemical reaction. An iron nail rusting, you guessed it. Cooking food, grapes fermenting into wine, even just breathing, it's all chemistry. It's not just something that happens in a lab with bubbling beakers. It's the invisible engine behind all the changes we see and smell and taste every single day.
All right, so if these reactions are everywhere, how do we actually spot one? How do we know it's a real chemical change and not just, say, water boiling? Well, you just have to know the signs. Think of yourself as a detective looking for the 4 telltale clues. Let's picture a classic example. If you take a strip of this metal, magnesium, and you light it on fire, wow. It doesn't just glow, it erupts in this crazy, brilliant white flame. And what's left behind? It's not a shiny metal anymore, it's this crumbly white powder. A totally new substance has been created. The very identity of the magnesium has changed. So that amazing transformation gives us our clues. There are 4 main things to look for. 1. A change in color. Think of that shiny metal turning into a white powder. 2. A change in state, like a new solid forming. 3. The evolution of a gas. Bubbles, like when you drop an antacid tablet in water. And 4. A change in temperature, like how a hand warmer suddenly gets hot out of nowhere. If you spot one of these, chances are you're watching chemistry happen right in front of you.
So, seeing a reaction is one thing. But how do we talk about it? Saying a magnesium ribbon burns in oxygen and it turns into a white powder works, but it's kind of long, right? To really study these things, scientists needed a shorthand, a clear, simple code to write down what's actually going on. So the first step was to ditch the long sentence and create a word equation. Look at how much cleaner this is. We just put what we start with on the left, what we end with on the right, and an arrow in the middle. Simple, direct, and way easier to understand at a glance. It just cuts right to the chase. And this gives us the basic grammar of chemistry. Honestly, the best way to think about it is like a recipe. The stuff on the left, the reactants, they're your ingredients. In our case, magnesium and oxygen. The arrow in the middle just means makes or yields. And the stuff on the right, the products, that's your final dish, magnesium oxide. Simple, right? Ingredients in, final dish out. But we can go even further. We can make it even shorter and more universal. We do that by swapping out the words for the official chemical formulas, the unique symbols for each substance. And boom, we get a true chemical equation. Mg plus O2 gives you MgO. Now that is the language of chemistry. A scientist anywhere on the planet can read that and know exactly what you're talking about. Okay, so it looks pretty neat, right? Clean, simple, but there's a problem. A really big one, actually. This equation, as it's written, it's a lie. It's breaking one of the most fundamental laws of the entire universe. It's just not telling the whole truth. And that brings us to the most important part of writing the story of a reaction, the balancing act. We have to make sure our equation is honest. We have to make it tell the truth about what's happening in the real world. This is the law. The one rule you can't break. The law of conservation of mass. It's super simple, really. It just means that matter can't be created out of thin air and it can't just disappear. For a chemical reaction, that means you have to end up with the same number of atoms you started with. You can rearrange them, for sure, but you can't create or destroy them. The books have to balance. Okay, let's try to balance one. We'll use a slightly trickier example to see how it works. Here we've got iron, that's Fe, reacting with water, H2O, to make a kind of iron oxide and some hydrogen gas. So right now, let's see if this equation is playing by the rules. Let's do a quick head count. On the left side, the reactants. We've got 1 iron atom. But look at the right side. Suddenly there are 3. Where'd they come from? And we start with 1 oxygen atom, but we end up with 4. It's like atoms are just appearing out of nowhere. This equation is totally unbalanced. It's breaking the law. So how do we fix this?
We can't change the formulas, but we can change the number of molecules. It's a bit of a puzzle. Okay, step 1, let's tackle that messy oxygen problem. We need 4 on the left, so let's put a big 4 in front of the H2O. Great. Now, step 2, that messed up our hydrogens. We now have 4 times 2, that's 8 hydrogens on the left. So to fix that, we need to put a 4 in front of the H2 on the right side. And step 3, the iron. We have 3 on the right, so that's easy. We just need a 3 in front of the Fe on the left. Phew. Okay, let's see if we did it right.
Let's check our work. We have 3 irons on the left, 3 on the right. Check. We have 8 hydrogens on the left, 8 on the right. Check. And 4 oxygens on the left, 4 on the right. Check. Perfect. Everything balances. Every single atom is accounted for. Now our equation is telling the truth. And here it is, the final, balanced, honest-to-goodness chemical equation. We can even add these little letters in parentheses to show the state of each substance, like S for solid and G for gas. So now we know it's solid iron reacting with water vapor or steam. So cool.
Now that we have this powerful language, we can do some really cool stuff. We can start to organize the entire chemical world. Just by looking at these balanced equations, we can spot patterns and start to group different types of reactions together. So let's look at one major type. It's called a combination reaction. And just like the name says, it's when 2 or more things combine to form one single, more complex thing. A great example is when you take calcium oxide, which is also called quicklime, and you add it to water. They react like crazy, create a single new product, and give off a ton of heat. And get this, here's a super cool real-world connection. That product, calcium hydroxide, is what people use to whitewash walls. And over a few days, it actually reacts with the carbon dioxide in the air, and it forms this thin, hard, shiny layer of calcium carbonate. And the amazing part? The chemical formula for that shiny finish is the exact same chemical that makes up marble. You're literally painting a tiny, microscopic layer of marble right onto your wall? How cool is that?
So there you have it. We've gone from just looking at something change to actually writing the secret language that describes how it happens. You know the clues to spot a reaction, you know the #1 law that all reactions have to obey, and you know how to tell the truth with a balanced equation. You now have the tools to read the chemical stories that are unfolding all around you. So next time you see rust on a fence, or strike a match, or even just take a deep breath, ask yourself, what's the chemical story that's happening right here, right now?